Hi everyone. In this video, we will be discussing the topic of dimensionless groups, and specifically, we will be sort of building on our first video and trying to sort of understand the independence of dimensionless group. Of how do we know that dimensionless numbers are independent, and how do we find that dimensionless numbers are independent? So, uh, just to briefly recap what we discussed in our first video, we discussed a problem where we had a droplet of diameter d, viscosity mu d, density rho d, and that droplet was being deformed by a stress tau, and the surface tension between the two phases, the droplet phase and the external phase, was gamma. So we said that we have five physical quantities: diameter d, viscosity mu d, density rho d, external stress tau, and surface tension gamma. And we said that we have five variables. So small n is 5, small m is the number of dimensions, mlt, 3 dimensions, mass, length, time. So using the Buckingham pi theorem, we can say that there will be two independent dimensionless numbers. And then we did the Rayleigh analysis 3 times to find n1, n2, and n3 written in here. So n1 was d into square root of tau rho by mu d, n2 was d mu d gamma by mu d square, and n3 was tau d by gamma. And then we said only two of these will be independent from each other. However, like sometimes students get confused of how do we even know that these numbers are independent. We have been given n1 and n2. How do we know that n1 and n2 are independent? And if we have been given n2 and n3, how do we know that they're independent? And if we have been given all three, how can we find the dependence between n1, n2, and n3? So that are the kind of questions we'll try to answer in this video. So let me start by sort of creating some questions that generally come in mind of students, and then we will try to give answers to them. Okay, so the first question that we will try to address is uh, how to know dimensionless numbers are independent. So the easiest way to think about this problem or this sort of question is we should just first look at the variables they are spanning. So the first part of the answer is that we should look at the variables they are spanning. So variables in the dimensionless numbers should be different. Okay, so for instance, let us look at the variables in n1. In n1, the variables are d, tau, rho d, and mu d. In n2, the variables are d, rho d, gamma, and mu d. And in n3, the variables are tau, d, and gamma. Now, if you think about this problem, if we choose any of the two of combination, let's say if I take n1 and n2, uh, n1 and n2 have different variables because this one has n1 has tau, whereas n2 doesn't have tau, it has rho d and gamma. So they have different variables which span them, and thus like so sorry, I mean to say that tau has n1 has tau and n2 has gamma. So they have different variables that are included in n1 and n2. So if the variables are different, then basically you have the dimensionless numbers have to be independent, right? So and if I choose n1 and n3, so n1 has d, tau, rho d, mu d, and n3 has tau, d, and gamma. So tau and d are common, but n1 has rho d and mu d, whereas n3 has gamma. So again, the combination is different, and similarly you can also do for n2 and n3. So any two of these three have different variables, and thus n1, n2, and n3 are independent if we take two of them at a time, right? If we take two of them at a time. Secondly, if it is possible that the variables may have same dimensionless numbers may have same variables. So if, although that is very rare, you will generally have the case of which variables are different, but if the variables are same, if the variables are same, their dependence within the numbers should be different. So it is possible, like, you may have some combination in which you have all five variables including in the number, uh, which is very rare. You may not see this kind of dimensionless numbers, but just to be complete, like, you should know this. So I'll discuss one small example of this case B, but most often you will just find the case A where variables in the dimensionless numbers are just different. So I said one thing in a sort of, which was implied here, that in n1, n2, and n3 they are dependent, they're independent with each other if I take two of them at a time, right? So that the number 2 was important here. So just so that nobody forgets, I will also write a question here: how many dimensionless numbers are independent? And for this question, we have done this in several times in the lecture and even in the videos and in office hours, and the answer is that this is determined by Buckingham Pi theorem, right? Theorem. And G, or capital N, is equal to N minus M, and in this case this was equal to 2. So I cannot say that N1, N2, and N3 are independent. I can say two of them, N1 and N3, N1 and N2, or N2 and N3 are independent. Just to be clear, that we should not start mixing. That first we have to check how many total number of dimensionless numbers are independent using Buckingham Pi theorem, and then if you are given two numbers, we can check if their variables are different or not. If you have been given three numbers, they cannot be independent, because Buckingham Pi theorem says that only two of them can be independent in this problem. So just to follow up on this, let us now start to ask, if you have been given two numbers, can we check their independent or not? So which of the following combinations are independent? So again, we have discussed n1 and the functional form of n1, n2, and n3, and we have again discussed that n1, n2, and n3 have different variables, and if we take two of them at a time, they are independent from each other, and only two of them can be independent using Buckingham Pi theorem. So now this is an interesting problem. I will sort of give you simple combinations, and we will try to find if they are independent or not. So first combination is n1, n2, n3. So can all these numbers can be independent from each other? They cannot be, because uh, only two of them can be independent using the Buckingham Pi theorem. If we have been given a combination of n1 and n2, can these be independent from each other? So if we go back and see that the variables in n1 and n2 are different, so yes, these are independent from each other, right? Then if we have been given n2 and n3, are these numbers independent? So if we again look back at the variables, n2 has t, rho d, gamma, mu d, and n3 only has tau d, gamma. So the variables are different. This has tau, this doesn't have tau. So again, they are independent. This is again just going back and checking at the variables. So this may look very simple, but now we'll start to do more interesting things. What about n1 square and n3, right? Now, why am I bringing this n1 square is this because this process is very flexible. You can actually choose n1 square, n1 cube, n2 square, 1 by n2. All of these are perfectly fine because these numbers are also dimensionless. However, for the sake of simplicity, we just use the power equal to 1, which is simple for us rather than trying to complicate things. So, but I'm just so that everyone is familiar, we can use n1 square. That is also a perfectly fine dimensionless number. So, our n1 square and n3 independent from each other. So what will be the variables in n1 square? n1 square will also have the same variables as that of n1. So what were the variables in n1? D, tau, rho d and mu d. And the variables in n1 square will also be d, tau, rho d and mu d, just the powers will be larger, right? But the variables will be the same. So in n1 and n3 also have n1 square and n3 also have different variables, and yes, they are independent from each other, right? Now what about a combination of n2 square and n2 raised power of 1 by 3? What about them? Are these two dimensionless numbers independent? So n2 square and n2 raised power of 1 by 3 will have the same variables because n2 square again will have the same variables as n2, which is d, rho d, gamma and mu d, and n2 raised power of 1 by 3 will also have the same variables d, rho d, gamma and mu d. So they have the same variables. So now we can go into case B. And what is the dependence within each other? So the dependence within each other has to be same. That the dependence of d and rho d. So let's go to n2. So the dependence of d and rho d within n2 square and n2 raised power of 1 by 3 will be same because they are actually just a different form of the same number. So they are actually not independent from each other. So they are dependent on each other. So this is not a valid combination. However, if I have a combination of n1 and n2 raised power of 1 by 3, is this a valid combination? Yes, it is, because again n1, the variables in n1 are first they are both perfectly allowed because they are just different powers of dimensionless numbers, and then the variables in n1 will be the same as variables in n1, and the variables in n2 raised power of 1 by 3 will be the same as variables in n2, which is similar to the case 2, number 2 here, n1 and 2. So these are also these are also independent from each other. Now let me also have something here which sometimes students get confused. What about 1 by n1 and n2? This is just an extension of what we have been discussing. 1 by n1 will have the same variables as n1, and the variables in n1 are different from variables in n2, like we have discussed before. So this is also allowed. So you can see that we have a lot of flexibility in this process, that you can have a lot of different powers to the same number, and basically we just use the simplest power, which is 1. We do not try to go into these 1 by 3 or square to keep things simple, but they are also perfectly allowed. However, as long as the two numbers you have chosen have different variables, they are independent from each other, and that is what we have been discussing in this problem. So the last problem I want to do is actually a little more complicated within the same thing, and that says n1, n2 and n1 square n3. What about these two combinations? These are two numbers, n1, n2 and n1 square n3. And how do we know whether they are independent or they are dependent on each other? So let me just write down again what was n1 here. n1 was rho d tau d by mu d. n2 is equal to d rho d gamma by mu d square, and n3 was tau d by gamma. So what will be n1, n2? n1, n2 will be d square rho d raised power of 3 by 2 tau raised power of half gamma by mu d cube, and n1 square n3 equal to n1 square n3 equal to d cube, actually d cube rho d tau the mu d square gamma. You can check, but this is basically what is the form you will get. So n1 n2 is this, and n1 square n3 is this. So why am I doing this problem is that uh, is to basically show you an interesting case, which is again very rare. You will probably never see these kind of messy numbers, because when we can have simpler numbers like n1 n2, why will we ever choose a number like n1 n2 or n1 square n3? But for the sake of completeness, I want to show you that in this n1 n2 the number of variables are actually 5. You have all the 5 variables here, right? And in n1 square n3 also you have all the 5 variables. So are these numbers dependent or independent? Though it may be tempting to say that, because both of them have all the 5 variables as the same, but if you closely look, they have different dependence. For instance, in n1 n2 gamma is in the numerator and mu d is in the denominator, whereas in n1 square n3 both mu d and gamma are in the denominator. So in this, the gamma is in the numerator and this is in the denominator. So in if these were the same sort of number, or they were powers of one another, in this, if gamma is in denominator, mu d should have been in numerator, or if mu d is in denominator, gamma should have been in numerator, which is not the case. Moreover, you can check that here d, d has a power of 2 and rho d has a power of 3 by 2. So if d had a power of 3 here, rho d should have a power of uh, 3 by 2 into 3 by 2, which is 9 by 4. I mean, just you can, again, they are not powers of each other basically, so they do not directly, cannot be said that they're exactly dependent on each other. So once you have the same variables, we check their forms, which is that are the powers, are they in some form ratios of each other, which they are not. So yes, they are also independent. This is again a very rare case. Most likely you will never encounter such cases, but just for the sake of completeness, this is how we can know whether the numbers are dependent or independent, right? So we have discussed several things in this video. We first discussed that how to know that dimensionless numbers are independent. We go and look at the variables that they span, and then if the variables are different, then the dimensionless numbers are independent. And if they're the same, we check their form, which is that their functional form should be same as within the variables should be same. Most importantly, Buckingham Pi theorem has to be valid. No more than capital N is equal to small n minus m numbers can be independent from each other. And then we discuss several combinations in which we discuss the flexibility of the system, where you can have n1 square, n2 cube. However, for the sake of simplicity, we just keep the power equal to 1. Now, before we just close this video, a quick question, just so that some students might be curious, and this is just for so that in case somebody is curious. So if we are given uh, 3 dimensionless numbers, whereas only 2 are independent from Buckingham Pi theorem, how to guess their dependence So in the problem question 3, we basically always had 2 dimensionless numbers, so we knew that they could be dependent or they could be independent. But in this problem in question 4, we are saying we have been given 3 dimensionless numbers, though we know that there will be only 2 independent dimensionless numbers. So if that is the case, how to guess the dependence? And basically uh, this is for the same problem. Let us say we have n1, n2 and n3, which I have written here. I will just write it down again. It is just to show you how to sometimes arrive at these results if you encounter them. Sorry. So I'm just writing down the n1, n2, and n3. So now in this problem we were told that there will be two independent dimensionless numbers. So how do we find the dependence of dimension numbers n3 on n1 and n2? So this is an extra number. If we choose n1 and n2 as a number, n3 has to be dependent on n1 and n2 because of Buckingham-Pai theorem. So how do we guess this? So to guess this, the way I think about this, and that's just one of the ways, you can think in another ways, is that in this n3, we want to get gamma in the denominator with power 1, right? So in n3, we want to get gamma in the denominator with power 1, and gamma is only in n2. So again, we start by looking at variables. So we know we want gamma in the denominator, and gamma is only in one of the variables. So n2 has to have power of -1, right? Has to have power of -1 because we want gamma in the denominator and gamma is in the numerator with power 1. Now the second thing is there should be no, and now we know that mu d square will be in the numerator because n2 is in power of -1, and there should be no mu d here. There has to be no mu d in n3. So what we want to do is we want to have mu d square of from n1 getting cancelling n2, the mu d which will come from n2. So you can just write this as n1 square, because in n2 raised to the power of inverse, mu d square will come in the numerator. In n1, the mu d is in the denominator with power 1, so you just square it to cancel it. This may appear very straightforward, or may be a bit confusing, but if you're confused, just write it down. I have just done it verbally, but you can write it down and see, oh, if I will get n2 inverse, then mu d will be in the numerator and there is no mu d here, so you want to cancel it out. And once you do the rest of that, you will see the rest of the dimensionless, rest of the variables, rho d, tau d, will all fall in place, and they will basically cancel each other out or come out in the perfect way. So this is one of the ways you can check the dependence from each other. So I hope you found this video useful. There basically the whole topic was to discuss the independence of dimensionless numbers, and then we solved several problems and discussed how we can find this relationship. So please feel free to give us any feedback, and see you in the next video.